Dans l'autre sens. Tiens, il y a c'est là, normalement. La première étape.
How do you want to do that?
First. Yeah. Okay. I can just use this next to the phone.
Okay. So let's check it out.
Well, yeah, I would.
Okay, so hello again, everyone. Thank you for coming back in the early time of the day on Sunday mornings. Extremely hardcore. So thank you for mentioning here. So it's my pleasure to introduce Tariq, who's has been a colleague of mine for a while now and a friend. So Tariq is actually not a neuro major or really a scientist. You're good. Yeah. Computing scientist. He's been working as a professional web developer for years, and he's been recruited at McGill to take the lead on a project for visualization on the browser. So it's part of that core team, including the C-Brain low-risk folks, which you may have heard of. We are developing like a kind of holistic computational platform that's fully web-based, with database, access to weak computing, and that will be the branch that takes care of the visualization for that platform. So thanks for coming, Tariq. Here we go.
All right. Hello, everyone. So like I said, I'm more from the technology development side of this whole business that we're all in. So I won't be talking to you about any research since I don't directly do any. What I do is create tools for the researchers at our lab to use to help them out. And one thing I've been very into is creating web-based tools to help the researchers do the work that they're doing. As I said, it's mostly visualization stuff for me, but I feel like there's really, there's been changes in the web ecosystem that has made it much easier to create really robust applications on the web in ways that I think are very conducive to the right types of research that go on here. So first, a little bit of history. So this is the very first web page that was ever made. So you can see it's just like basically text, header. You can organize your information a bit, links, but that's about it. Like not a lot to work with there in terms of app development. Then a little later, then we got images. We got some color that we can stick in. Still a little pokey, but it's moving forward. Then we got to the point. So Google Maps was really like one of the first widespread, widely used, what we call web applications, where you had dynamic loading of data. It was interacting with a back-end database loading those images. So you could really use it almost like application that was on your that you installed locally. And now, recently, we have a lot of new technologies that have come out that have made it possible to build these really like full-featured applications that basically run in your web browser. Oops. Oh yeah. Okay. So, why is the web just an interesting platform to work with? So one is that it's everywhere. So right now, like we talked to you about Brain Browser, this is an actual instance of Brain Browser that's running in this presentation because this presentation is done in HTML. So I can just insert this visualization that's visualizing some actual data right into the presentation. Like it's essentially ubiquitous. It's extremely powerful now. You have the type of processing that can be done, the type of graphical capabilities that you can get out of a browser are much higher than they used to be. It's very easy for users to get in. So pretty much everyone now has a web browser. They don't have to install sockets, there's no worrying about dependencies, the libraries that are missing or not. And another thing is that you never have to, the users never have to update it directly. Like you push a new version of your app out there, and basically anyone that accesses it through their browser will have the latest version that you created. And for those of us that actually develop the apps, it's very easy to do so. Like this is basically that visualizer, that little instance of Brain Browser I showed you before. Here, this is the code that runs it. Like it's just about, I think it's 12 to 15 lines of code to get that thing up and running. Okay. All right. So we talked a bit about like generally like what would you want or what makes the web platform interesting. Now, how does it apply directly to neurology research? So these are the things that are interesting about it. Like that there's just a ton of data coming into that people are dealing with these days. It's very difficult to move around. It's kind of all over the place. So using the web platform or these web applications, you can access the data remotely instead of having to move it to your machine and then install something and visualize it. Because this is really the key thing about when you're thinking about developing stuff for the web is the connectivity. That's what it brings. Like it's really just everything kind of connected together. In terms of sharing your tools with other people, again, it's online. They just access a URL and they have that tool. Like they don't have to install it locally and figure out how to get the dependencies on their machine. For sharing data, I find this very interesting. Like if you want to distribute your data to other people, instead of just giving them this blob of binary data volumes or whatever it is, you can actually share it, and which I'll show you an example of, by giving them some tool that allows them to kind of explore that data remotely, which I think is an interesting application. And then obviously, because of the connectivity, collaboration is much easier. You can be working together on the same data and just accessing it remotely. So the case study that I use is I don't know if anybody knows about this macaque data set. So the macaque data set, just to give a little bit of background, it's like this big 1 terabyte data set, 6.3 million data maps. They're essentially encode kind of connectivity information. The brain actually might be easier to find. And this is built using the Brain Browser. So basically what happens is it loads this surface, and I click here on some point on the surface, it'll load a map, and basically what that map. So what this coloring represents is for the point I click, it's for all the other points on that surface, their correlation with that point I clicked in terms of, in this case, it's cortical thickness. There are a few other measures in there. So it's this huge data set that would be a pain to move around and visualize. Otherwise, that we've been able to create this fairly intuitive interface for people to just go and explore it from at home, just by opening up the page in their browser. All right. So what changed? I want to go through like some of the specific technologies for users in the world, the developers here, for most of us. But what's changed in the browser, in web development, that has enabled this, these type of applications to be built? So the first thing is, okay, the language of the web, the programming language is JavaScript. So as a starting point, JavaScript has just become a much more robust language for developing complicated applications. Part of it is the speed. So when Google brought Chrome to the market, they made a big push to make their JavaScript as fast as possible. Their JavaScript engine is called V8. So it was like an order of magnitude faster than anything that existed at that time, which just, the speed just allows you to do things that you weren't able to do before. And then Mozilla now, the makers of Firefox, have this very interesting project, Atom.js. So what that is it's a highly optimizable subset of JavaScript that they have gotten running. So basically what they have is a compiler that compiles C or C++ code down to this subset of JavaScript, and are getting it running at about 80% of what it would run natively. And if you know what's kind of the fact that this is running in a virtual machine and the whole bit, and you have the overhead of the browser, like that's really insane performance to have from a web application. And then in terms of the language itself, it's become much more robust. So you have, for those who don't know, ECMAScript is the name of it's a specs basically for JavaScript. So you have new versions that come out every once in a while. The current one is 5. The next one coming out is 6. And what they've done basically is add a lot of features, like you organize and modularize your code. And are deprecating a lot of dangerous features, basically, that allow you to create bugs that were hard to find and stuff like that. So it's just become a much better language to work with. So you have the 2D canvas. I don't know if people have heard about this. So the 2D canvas is just a high-performance scriptable drawing surface. You can draw just primitives on there or shapes or whatever. And one interesting thing it allows, which I use for another part of the Brain browser, the volume viewer, that allows you to get in and really do image processing at the pixel level and images that you're dealing with. So I use that for like colorizing the slices I get out of volume and stuff like that. WebGL, which I'm sure people have heard of. It's basically an API that allows your browser to talk directly to the graphics card on your computer. And this is what allows, like we're seeing in the Surface Viewer, the high performance 3D graphics where you can render a lot of polygons. Web workers, very important also. We use it quite a bit in Brain browser. Its background is that JavaScript is by design a single-threaded language. So what that means is basically when you're writing your code, it always executes one thing after the other. You can't be doing two things at the same time. And this includes the rendering and the user interface will all be running on this same thread, which is problematic if you want to do any heavy computation in the browser. So this new API web workers allows you to actually do multi-threading, where you put a task out to be done on, it can be done on a separate CPU or whatever. It can take advantage of having several cores. You can offload those compute intensive tasks, and then you give it a callback and continue running when it's done. So this allows so for in-brain browser, just for example, parsing the big geometry files or object data will be done in a web worker. And then these are two technologies. I'll admit that I haven't worked with them directly, but I think they could be very interesting for like collaborative applications. Socket, what it does is it allows full duplex communication between the browser and the server. So what that means, basically the normal way of you interacting with the server is your browser will make a request. So it's one way. You have to initiate the request, and then the server sends back data. What WebSocket does is it lets the server actually initiate communication and tell your browser that something has happened. So you can imagine like a chat application, like if the person you're talking to sends a chat message, the server, it'd be nice if the server could just say, tell your browser, okay, there's a new message, and it updates it right away. So that allows for these kind of like, you could create like collaborative environments where it's being updated for both people at the same time. And different protocol, but similar use case, at least that I have in my head, is WebRTC, which allows, instead of going through the browser, you can have two browsers, going through the server, you can have two browsers that are communicating with each other directly. And again, yeah, for collaborative applications, I think that could be very interesting. That's it. Thank you. Yeah, I mean like the.
I mean 3D with the glass. Like you got a 3D.
Oh,
So,
yes. Like there's. So it would stuff like that. If you want like where it's. So I'll just show you something very quickly. I can. How do I get out of this?
Are you asking because you want to view the brain with 3D glasses? Like in like augmented state where you turn your head and you're navigating inside the
Yes.
brain?
no,
Oops.
no, just on the screen.
But if you want to do that, I would recommend using an Android. And there's a small device made called cardboard. I think it costs like $5. But if you put an Android in, you can use the Android to navigate states with your eyes.
Yeah.
So you put it on your eyes.
Yeah.
And you can
But it was more asking like with web face.
yeah, but the web app it could be a web app. You could use Brain browser and navigate Brain browser using the
Okay. So there's a couple things. Yeah, I got this. So seeing something in 3D will depend on a couple of things. Like you can do basic, like you can do the red and blue just by having the glasses, and you'll render the two images slightly offset, which I actually have implemented here. There, have this view. Yeah. Yeah, everybody has 3D glasses in the room. You can see this coming right out of the screen. For the more like, what do they call it? Where's the, but it would depend on the monitor as well. Yeah, but you could essentially render it so that it's rendering to one channel or the other.
you have control over everything, right?
Yeah. Yeah, it's basically talking to the graphics card. Like they have, I don't know if you guys have heard of the Oculus Rift. Like it's Mozilla working on that mostly now, but I think Google will follow suit where they have APIs to talk to the Oculus Rift as well. Rendering, they're coming for that. So VR kind of set up. Anything else? All right, thank you. Yeah, sure.
I want to install it on my computer. I just have to use
Sorry, if you want to install. Yeah. So it's all online. Like so, this if you go to this site, it's a little bit of a long URL. But if you look for Brain browser on the
If you Google Brain browser, you're gonna get to this.
yeah, and it is all on GitHub. So you have here. So this Brain browser site will have like the API documentation and some like instructions about how to set it up. And if you go to what is this? Yeah, and you have here that it has a little bit of like in the API documentation on the GitHub repo, you'll find some getting started information.
Can I ask one question?
Yes.
In your estimation, how easy is it for students to learn JavaScript versus other programming languages?
Sorry.
How easy is it for students to learn this language compared to other languages?
JavaScript. I think it's a really great place to start. There's a lot of traps in it. Like it's a very idiosyncratic language, if you want. But one of the things is like I've actually taught like people JavaScript and other like programming in general. And one of the very nice things about it, which doesn't have to do with its difficulty, but is just that you can really get a ton of very nice visual feedback to what you're doing, which is different from if you're learning C and just getting like a printout of the Fibonacci sequence or something like that.
Or a cycle?
Yeah, also. Yeah. I do think it's a good place to start the program.
Thank you. We will move on to Jalen's second presentation.
Stickers? Okay.
So, as a background in physics,
Yeah.
and a PhD in biomedical engineering at the University of Technology. Last year, I was assistant professor at Columbia University, and he just arrived here in Montreal at the Performance Center at Concordia University, and he's also here to this center here. So I think it's main expertise in functional brain imaging. So we'll talk better than me about that.
All right, stickers briefly. Friend of mine in France, he left science and computer engineering for a surfboard company, biodegradable and eco-friendly surfboards. Husqvarna, buy a plot of land with trees, then cut the trees down. My favorite radio station, and this is a store in the Basque Country that sells awesome t-shirts. So just to try to provide some balance in that life. So I want to talk more about an idea and a thought process than actual research. So I kind of have a toy example that I'm going to be going through. It's going to be basically my entire talk, just to kind of advocate for my own personal thought process. So I'm hoping this works as far as in case you know. And I'll be here to describe Sunday morning, I'm going to try to be exciting. So, all right. So I want to kind of advocate for people going beyond the correlation matrix. And I want to discuss going beyond the correlation matrix and going beyond the study of correlation matrices, and to incorporate multiple imaging modalities and to really incorporate cognition and behavior, to try to use brain imaging as a tool for understanding behavior, understanding cognition. We're just describing the relationship, like, or these two different brain regions are correlated with each other. That's nice and interesting. How does that describe something that's going to be impacting an individual's life? Like, so, as the study of cognition and behavior. So I'm going to start with the correlation matrix. What you can see right away just from looking at this is there's a lot of structure in it. So if we break that up, identify the parts. This is from 206 people over the course of an aging between 20 and 80. And the piece of the data in this correlation matrix are cognition. We have cortical thickness, derived from free surfer, subcortical volumes, also the amplitude of cortical brain activity within these different regions of interest, and also within cortical areas and subcortical areas. And that's people doing a matrix reasoning. So the first thing you can see is within modality, the correlations are quite strong. Yes.
Can you repeat the task again?
It's called a matrix reasoning task. So it's an executive function task. So it's a cognitive task. Okay. So the next, so here what I did is I took the previous big correlation matrix, broke it up into the three pieces, and then rescaled the bottom left-hand piece. On the previous slide, it looks very green and very uniform. But if we rescale it, so now the correlation value is 0.4 minus 0.4, we can see even within that, there's a lot of structure. And this is the correlations between structure and brain activity. So the thickness of the region related to the amount of amplitude of brain activity in that region. Okay, so down here. So what I'd like to point out is, so if you look, at least one region here where there seems to be this, the volume of this region is related to brain activity in a lot of different other brain regions. So it seems like this is one right here. The volume of this region seems to be very important to the functioning of the brain elsewhere. So I'm advocating for people to start looking at this sort of behavior, with structure and brain activity, use correlation between modalities. Now, I just want to back up that top left. So this is cognition instruction. So these first 12 columns are cognitive performance on 12 different tasks. So basically these 12 columns. So in this range here, that's the relationships between cognition and cortical thickness. And then down here, I want to focus on just the relationships between cognition and subcortical volume, just to try to focus on something specific. So row 11 here is the volume of the left hippocampus. And this second column is a cognitive test called the selective reminding test, the selective reminding memory test. So we would expect there to be a fairly strong relationship between memory and hippocampal volume. They're always implicated together. The correlation value here is 0.15, which is fairly low. So, I mean, that kind of asks the question, well, why is it so low? I would expect it to be a lot higher. So it turns out, if we put in some other variables here, this column here is vocabulary skills. So one aspect of my background and training is this studying the idea of research. That things that people do in their daily life or even across their lifespan affect how they're affected, or alter how they're affected by aging. So education, for instance, is very good for us. Physical activity is very good for us. All the things that the doctor tells us are really good for our hearts and our brains. And this is what's led me to come up here to Montreal to be working at the Performance Center. But it's this, so I didn't just arbitrarily look at everything. I specifically looked at vocabulary skills because it's simply strongly related to this idea of research, providing some sort of protection. So let's go to a scatter plot. We're at hippocampal volume versus memory score. And color-coded the dots related to the so you can see all the young people, they're all up here with higher memory scores and higher hippocampal volume. And the older adults they're getting down here with the hippocampal volume, lower hippocampal volume, lower memory score. But what you can see is there's a huge amount of variability. I mean, we have some of these older adults, they, like this person here, their hippocampal volume is the smallest of this entire group of 200 people. But their memory score is not as low as this person, but still has much larger volume. So now, what I've done here is I still have hippocampal volume, and this is basically memory score, but I've broken people up based on their vocabulary skills. And I'll look at the relationship between volume and memory score as a function of vocabulary skills. And so we've got three here, so low vocabulary, middle, and high. And the dotted line and the green line, they overlap with each other. And that's kind of the average relationship. They slope the relationship on the previous slide, both scatter plots. But what you can see is, look at the blue line first. These are people with low vocabulary skills have a fairly strong relationship between hippocampal volume and memory score. Then if we look at people with the high vocabulary skills, the relationship between hippocampal volume and memory is not there. No relationship. So now you're all confused. What does this mean?
What is your test?
This is
Can you repeat the question?
what was the memory task? It says,
And I have the same question for what's the vocabulary test?
okay. Okay, the vocab, well, we'll start with the memory test. The memory test is a selective reminding test. So the participant is sitting with the research assistant or the researcher. and they're told, all right, here's a list of, I'm going to read you 12 words. So the participant gets read the 12 words, and you have immediate recall. Okay, now I want you to tell me what words you told. So then you get a score how many of those did you actually know. Then the researcher will say, well, you missed these 3 words. I'm going to tell you those 3 words. And now tell me what those words, what the 12 words are. So then you go on, all right, now we're going to do another task. So you've got 4 or 5 minutes of some different tasks. You go, remember the 12 words I told 5 minutes ago? Can you tell me what they were? So then you end up cycling like this. So you get reminded of what those 12 words were, which ones you missed, and you ask to recall them again. So it's memory testing it. You end up having immediate recall, 5-minute recall, 1 hour recall. And the vocabulary tests, that we use the North American reading test. And you're given a really long list of different words written on a piece of paper, you have to pronounce them. So your level of education and vocabulary skills related to how well you pronounce these words. And some of them have if you just read the word, then you'd be pronouncing it wrong. And I can't remember any examples off the top of my head right now. But there's certain words that if you know what the word is and you know what the proper pronunciation is, you'd say it correctly. Versus if you just read what the letters were. Does that make sense?
Yeah, but so the first task is a memory task based on language. You're using words. You use memorization of anything else.
Correct.
For that? Why did you choose a task that was based on language?
I mean, it's part of our battery that we use.
Okay.
I mean, so yes, there is, I guess by design, there's a relationship between the two. Yeah. Yes. But this, I mean, this also works, is what I'm calling vocabulary test. I'm calling that a reserve measure, a proxy for cognitive reserve, and it works equally well with education. So, and what's another nice thing is with cognition, as we age, memory decreases over our lifespan, speed of processing decreases over our lifespan, executive processing decreases, vocabulary skills stay fairly constant and even increase across our lifespan. So that's why your grandmother will always beat you at scratch. So, all right, so what does this mean and what am I trying to say? This was supposed to be a dynamic slide. Anyway, so at the top, plotting age versus hippocampal volume, and you can see as we get older, hippocampal volume decreases. It's fairly constant at the young ages, then starts to decrease. We also have, as age goes up, our memory score is also decreasing. So the questions I'm really asking are, is there a causal relationship? Does the memory score decline because hippocampal volume decline? So is there a causal relationship? It's slightly, and it's complicated because of things such as vocabulary, what I'm calling research. So declining volume affects memory for the people below vocabulary. However, people with the higher vocabulary skills, hippocampal volume does not affect the memory score. So my title was saying I was going to study path analysis. So basically what I've done here is this sort of very simple path analysis. We've got age, hippocampal volume, memory scores, but this relationship here is affected, moderated by vocabulary skills.
Or education. Because that may be a proxy for education.
Correct. Or education is the mechanism by which vocabulary skills increase. So what I'm doing with my research career is kind of doing analyses like this. And I've developed a whole suite of code which does these sort of analyses at voxelized level. And everybody else has to get put this on before. So, but now the question is, okay, if increased vocabulary skills, increased education are kind of offering some sort of protection, what's the mechanism for it? So could the mechanism be down in here? So could the interrelationships, or how the relationship between declining hippocampal volume and brain activity, could that relationship be the mechanism by which vocabulary offers protection? Or could it be in the sort of the interrelationships between our brain function? So I guess what I'm trying to say is, if somebody's interested in studying network analysis, doing network analysis on the resting state brain activity, instead of just saying the networks of brain activity and resting state differ by the age groups, or differ between your population, related to something else, related to a covariate, explain something, you could explain why more education is good for us. Could that be the mechanism of education? So I'm advocating to bring more values together and related to some behavior, some sort of outcome measure. That's it. Thank you.
Are there immediate pressing questions? And just a remark, there's several people here working with me very interested in that. For sure, the type of software we develop could work with this type of estimation, where we're just looking at the correlation and frame them between groups, do more like past analysis on those connections, the stupidity test.
That's what I'm advocating for. Move back.
Yeah.
But also, I mean, this is very simple, but why can't it be structure here, cerebral blood flow here, FA matched up here, and say, how do we best explain declining memory?
Well, if you go back to your matrices, there's I think the idea we are building on that you have a lot of structure in there. So you can really reduce the dimensionality of that to several scales. So here you have maybe 3 guys, the top one, big one, small one, and maybe I can study the interactions everything at this scale, or maybe there are interactions that are small, and then I can try another scale. Or if you reorder properly the big guy, you're going to find 3, 4, 5 plus the big ones in there. So then you can start learning for interaction higher dimensionality. And we have our software is essentially that with multi-scale, looking to more analysis and currently looking at for interaction. So we have a structural connectome and a function connectome, and we use multi-scale decomposition to study interactions. But you could apply these things and I think something should definitely work.
Yeah. That's why what I'm doing was, trying to focus on this sort of simple, very simple path, and then this block can be anything. This could be a connectivity analysis, a connectivity result, but then also putting in these interaction effects, where this brain measure interacts with some other behavior or cognitive measure to predict some outcome. And then this also could have an effect on this relationship.
All right, so
So we have just finished the second Ignite session, so maybe we can just move on upstairs and continue the work of today. Thank you very much for
Is there any interaction?
I'm just going to check up Android app and
If you guys are curious about that, we're having a hackathon this weekend actually with cardboard. We're gonna have a bunch of cardboard available, and you can totally bring either drive by or bring a browser and just navigate using the Android. You just use the barometer of the Android and the gyroscope, and that helps you with something
and then you get this structure and it was controlled by the cardboard for a lot of time. Yeah, and actually that could be used for art. The evolution, your medicine.
So let me give you a